Have you ever charged your phone, replaced a remote battery, or marveled at how a car engine starts with a twist of the key? All of these are powered by electrochemical cells, tiny energy factories based on redox chemistry. In chemistry, electrochemical cells are classified into three types: primary, secondary, and fuel cells. Primary cells are one-time use devices. Once the chemical reaction is over, the cell is dead. A common example is the dry cell used in torches. Secondary cells, on the other hand, are rechargeable. They allow us to reverse the chemical changes by supplying electricity. That's what happens when you plug in your phone. Fuel cells are slightly different. Here, fresh reactants are fed into the cell continuously, and products are removed continuously, making them ideal for sustainable energy systems. Each type serves a different need, whether it's convenience, reusability, or efficiency, and understanding their chemistry helps us use them wisely. Imagine a battery that doesn't just die but revives itself over and over again. That's the magic of secondary batteries. Secondary batteries are special because the redox reactions inside them are reversible. By applying an external current, we can restore the original chemicals and reuse the battery multiple times. These batteries play a central role in backup power systems, solar energy storage, laptops, and electric vehicles. A good secondary cell has three critical features: a stable voltage output, a high number of charge-discharge cycles, and efficiency over time. The most common example is the lead storage battery, a workhorse in cars and inverters. Let's look at how it works next. Let's take a deep dive into the lead storage battery, a classic example of a rechargeable battery that's been powering cars for over a century. In its construction, the anode is made of lead metal, while the cathode is made of lead dioxide, which is lead 4 oxide. The electrolyte is a 38% solution of sulfuric acid. When the battery discharges, the following reactions occur. At the anode, lead solid plus sulfate ions in aqueous form gives lead sulfate solid plus 2 electrons. At the cathode, lead dioxide solid plus sulfate ions in aqueous form plus 4 hydrogen ions plus 2 electrons gives lead sulfate solid and 2 water molecules in liquid form. Combining both, the overall cell reaction becomes lead solid plus lead dioxide solid plus 2 molecules of sulfuric acid in aqueous form produces 2 molecules of lead sulfate solid and 2 water molecules in liquid form. This redox reaction releases energy that powers electrical devices. When we recharge the battery, the reactions reverse and we get our active materials back. So why is the lead storage battery still so widely used despite newer technologies? One reason is its ability to deliver a steady voltage, about 2 volts per cell, even under high current loads. Multiple such cells are connected in series to create 12-volt batteries used in cars. Another advantage is its robust design and affordability, making it ideal for automotive and home applications. Because the reactions are reversible, it can be used and recharged hundreds of times. However, there are drawbacks. Lead is toxic and the battery is heavy. Also, a phenomenon called sulfation, where white lead sulfate crystals block the electrode, can reduce its efficiency over time. What if we want something more durable and longer-lasting than lead batteries? That's where the nickel-cadmium cell comes in. The anode here is made of cadmium metal, while the cathode is made of nickel hydroxide, specifically nickel 3 hydroxide. They are separated by a porous layer soaked in sodium or potassium hydroxide. During discharge, the overall reaction is cadmium solid plus 2 molecules of nickel hydroxide 3 solid forms cadmium oxide solid plus 2 molecules of nickel hydroxide to solid and 1 water molecule in liquid form. These cells are compact and can be built in a jelly roll format, which is great for portable electronics. But cadmium is a toxic heavy metal and manufacturing costs are high, so their use is mostly limited to special purpose equipment. Now, let's look at a futuristic battery that doesn't run out of chemicals, fuel cells. Unlike normal cells, fuel cells continuously receive fuel and oxidants from the outside, which means they can keep producing electricity as long as the inputs are available. One of the most famous fuel cells is the hydrogen-oxygen cell, used during the Apollo space missions. In fact, the electricity for spacecraft instruments and even the astronauts' drinking water came from this cell. The beauty of fuel cells lies in their clean and direct conversion of chemical energy into electricity with high efficiency and minimal pollution. Let's break down how the hydrogen-oxygen fuel cell works chemically. At the anode, hydrogen gas reacts with hydroxide ions to form water and releases electrons. The reaction is, two molecules of hydrogen gas plus 4 hydroxide ions give 4 water molecules in liquid form and 4 electrons. At the cathode, oxygen gas reacts with water and electrons to form hydroxide ions. That reaction is, 1 molecule of oxygen gas plus 2 water molecules plus 4 electrons gives 4 hydroxide ions in aqueous form. Combining both, the overall reaction becomes 2 molecules of hydrogen gas plus 1 molecule of oxygen gas gives 2 water molecules in liquid form. These reactions take place at porous carbon electrodes infused with platinum or palladium catalysts. This cell achieves an energy conversion efficiency of about 70%, far superior to traditional combustion. As long as fuel and oxidant are supplied, this electrochemical engine keeps running silently and efficiently, making it an exciting technology for clean energy. So let's quickly summarize what we've explored. Electrochemical cells come in 3 main forms: primary, secondary, and fuel cells, each with unique chemistry and purpose. We discussed how the lead storage battery works through reversible redox reactions, making it suitable for cars and backup power. We explored nickel-cadmium cells as a more durable option and concluded with the elegant design of hydrogen fuel cells, which could be the cornerstone of future green energy systems. I hope this session helped you see how chemical energy can be harnessed, recycled, and even made sustainable thanks to the power of redox reactions. Catch you in the next topic, where we'll dive into electrode potentials and the exciting world of electrochemical series.